assembly of nanoparticles into 2D well-ordered monolayer or 3D nanoparticle arrangement is required and are fundamentally interesting due to a new physical, electrical properties and due to a new application like magnetic data storage media or spintronic application. But deposition of nanoparticle to get 2D arrays or 3D arrays is a complex process and it occurs under a specific condition. Therefore, one has to find a fast, simple method with a low cost that match the required needs of industry, which was the main task of my PhD research. Hello, or in my mother language, Assalamu alaikum. My name is Asmaa Qdemat. I finished recently my PhD research from Jülich Center for Neutron Scattering Studies, JCNS-2, under a supervision of Professor Thomas Brokel and Dr. Emmanuel Kanzena. Main aim of my project was to get highly ordered 2D assembly of nanoparticle and 3D assemblies of nanoparticle, then to investigate its structural and magnetic properties by using different X-ray and neutron scattering techniques. Today, I formatted my talk to clarify to you at the beginning why I carried out this project, what can be done with it in the future. So I hope you will enjoy hearing my talk in the next 15 minutes. During my talk, I will start not with my research. I will give first a general brief introduction about nanoparticle, why I choose to work with nanoparticle. Then I will move with you to give a short introduction about my project. Also, I would like to answer 3 questions in my talk. One of these questions concerning my past, what I did in the last 3 years. And second question about my present situation, what I'm doing now after my PhD. The last question concerning my future vision of my research, what can be done, what I'm going to do with my knowledge in nanoparticles. Let's start with the word nano. What do you mean by nano? Sure, this word is not strange for most of you. Nano can be referred to nanotechnology, material, particle, object. But I'm going to today to focus only in nanoparticles because these particles used widely in various fields recently. Nanoparticles are very small particles having one or more dimension of order 100 nanometer or less. I remember just before 2 years when I joined a conference in Korea about GSAS technique. Then I just joined a talk of a scientist. He is working on synthesis of nanoparticle. And at that day, he said, now we can have a periodic table of nanoparticle after this advanced synthesis technique. And I like the picture that he showed that I'm showing today. And why he said that? Because if we just imagine during synthesis of nanoparticle, we can control a lot of parameters like the size, the shape, the surface modification. So I'm going to say like one day we can have a periodic table of nanoparticle as a periodic table of chemical elements. Okay, just to come closer to the meaning of nanoparticle, let's take these simple examples. Imagine that we have a sheet of paper. It would take 100,000 nanometer to match the thick of this sheet of paper. Or just imagine a human hair. It would take 80,000 to 100,000 nanoparticles side by side to match the thickness, the width of the human hair. Sorry. Okay, why I choose nanoparticle? Why I did not work with other material? Nanoparticle, if this particle it just form a new conventional material, then sure it will show a new physical, optical, electrical properties. And as we know, as the material size it decreases, that means we have a larger surface area. And means nanoparticle have a larger surface area to volume ratio, which make it more reactive and which make it also easier or faster dissolution. Nanoparticles, what's the difference between nanoparticle and bulk material? Nanoparticle can be considered as a building blocks like atoms for crystal or for nanoparticle superlattice. One last thing, it can also be considered as a bridge between bulk material and atomic or molecular structure. Okay, sure, most of you know that now the research in nanoparticle is gaining much interest day by day. Why? Nanoparticle used or evaluated for different type of fields, application in different fields like optical, electronic. So I'm not going in details due to the time limit, but nanoparticle can be used in different industrial application, in food agriculture, in environment, and also can be used a lot in biomedical application. One thing I want just to take a few seconds to say nowadays nanoparticle can be used to treat the COVID-19 coronavirus, which is things that the whole worldwide suffering from it nowadays. Okay, so just quickly, I found one nice research recent that they are using a test based in using gold nanoparticle to check if the coronavirus is there or not. And this, the main basic of this test that there is a gold nanoparticle attached with a molecule that binds to the novel coronavirus. If the virus is there, then the color of the gold nanoparticle, it will change to a blue color and a precipitated it's noticed. But if the virus is not there, then we just get the original purple color. Also, a lot of research just published last month about how we can use nanoparticle to come closer to a treatment for this virus. And I recommend it, if you are interested about this topic, to go through this publication, nice publication that mentioned a different type of metallic nanoparticle. Okay, now I finished from the general introduction. I'm going to introduce to you what I did exactly with nanoparticle. As I said before, idea to get 2D well-ordered monolayer over a large area, or 3D arrangement, then study the structural and magnetic correlations of this structure. Regular arrangement of nanoparticle, it's important. Like, first of all, in order to study the magnetostatic interaction between this nanoparticle. To the best of my knowledge, up to now, no research published about the magnetostatic interaction between nanoparticle of highly ordered arrangement. As I know, just one, in 2011, they published this research, but about macroscopic magnetization measurement only for short range order. And also due to the interesting application of this system that can be used for magnetic data storage media by increasing the capacity of the hard disk drive, or can be used also for spintronic application where we can use also the spin to store the data and process the data. So to get a highly ordered arrangement of nanoparticle, I deposit the different shape of nanoparticle, different type, on a pre-structured substrate, and this substrate were fabricated using different top-down and bottom-up methods, and I choose to work with this substrate because it can be used as a template for assisted self-assembly of magnetic nanoparticle. Sure, I use a lot of techniques during my research, but I'm going to mention two main techniques. One of these techniques known as GSAX, grazing incidence small angle X-ray scattering. The idea behind this technique is that the X-ray or the neutron beam directed toward the sample surface with a very small shallow angle, alpha I. And from this technique, we can get access to the lateral correlation between nanoparticle and vertical correlation. And also we can get information about the size distribution, spatial correlation. Other technique, nice technique, that you can get information about magnetic depth profile or nuclear depth profile, means we study the nuclear scattering length density as a function of the height of the nanoparticle, which is called a neutron reflectometry. So the neutron comes to the sample and we study the change of the magnetic scattering length density by changing the incident angle. Okay, just this is a briefly, I don't want to say a lot about the technique, and other techniques I used a lot actually. Like to get information about the surface, local information, I use a lot of microscopic technique, such as scanning electron microscope. Also, I use small angle X-ray scattering, which is performed at Galaxy. Gallium anode low angle X-ray scattering, a nice machine at JCNS-2, high brilliance X-ray source, has a flux comparable to the second synchrotron generation. And the other, also to get information about macroscopic magnetization properties, I use superconducting a quantum user interface device. is my work is new or there is a previous work of it? In 2011, Sabrina Dish found that we can get ordered arrangement of magnetic nanoparticle by applying a magnetic field. But she found that just over a micrometer length scale, not over a centimeter square. And what I did during my master, I deposited 20 nanometer spherical iron oxide nanoparticle in a pre-structured silicon substrate and on sapphire substrate structured by annealing. And what I found that the long-range literal order can be obtained if the size of the structure in the same order of magnitude as the particle diameter. The work is published last year, and we characterized the system using different technique, mainly GSACs to get information about the literal ordering of the nanoparticle inside the grooves, and magnetization measurement to get information about how the particle interact together inside the grooves. During my PhD, the idea was to optimize the structure using different type of nanoparticle, different shape. First one, I used silica nanoparticle with a spherical shape, and this particle synthesized by collaboration with Johan Bottenhuis from ICS Institute. And also I used cobalt ferrite hemispherical nanoparticle or truncated sphere, and this particle also synthesized by collaboration with Joseph Portale from University of Groningen, Netherlands. And also I used a nanoparticle with a very nice shape, which has a shape, a cube with rounded edges, or what is called now superball, means the shape between a sphere and a cube, two type of particle, cobalt ferrite and iron oxide nanoparticle with different size. And at the beginning, to check the morphology of your particle, how is the size, how the shape look like. Then I use the microscopy technique. I'm just showing some examples for each particle. Like for silica nanoparticle, I just showing the ECM, and we can use also AFM to get also the 3D image, how the particle looks. I use it for cobalt ferrite because, as I said, we have a hemispherical particles. And for the cubic or the superball nanoparticle, I'm showing 10 images. Also, I use SACs. SACs, it gives also information about the particle morphology, but it gives average statistical information. What we got from the measurement, we got this nice colorful image, 2D detector image, and by doing a radial averaging of this picture, you can get access to the 1D data, intensity versus Q. And by fitting the data to a theoretical model, then you can get information about your particle shape, the size, and the polydispersity. And other examples also I'm showing for the superball nanoparticle, and I show here that I fitted the data using different theoretical model, sphere, cubic, and then a new form factor superball. To get also information about the magnetic behavior of the nanoparticle, I'm just showing here one example for the iron oxide nanoparticle. What's nice behind that? That we can do a magnetization measurement for a liquid nanoparticle by filling this liquid inside a quartz ampoules, which prepared at JCNS-2, and you can also measure at squid a magnetization as a field dependent or a magnetization as a temperature dependent. For sample preparation, I can say I use a difficult method and I use a very easy method that can be done at any lab. First, top-down method just to get the pre-structure substrate. Two methods I use: electron beam lithography, which is done with a collaboration with Helmholtz Nanoelectronic Facility Institute at Jülich, and I used also the displacement Talbot lithography, which is done by a collaboration with Olita Company, Switzerland. For depositing the nanoparticle in this structure substrate, I use what is known bottom-up method. First method, drop casting, which is very easy, can be done in a simple lab. And spin coating, which is mainly depends if you have a spin coater, then you can deposit your particle in the substrate and just control the speed and the time. Also, I use a dip coating. It's just the idea, immerse your sample inside the liquid, and you have to be careful just about your hand movement, the time you just put sample inside the liquid, and the time when you take it out. And last thing, I use also the magnetic field assisted self-assembly just to help the nanoparticle to order inside the grooves. Okay, I want to say I will not show a lot of details about my result. I will just show highlights. And if you are interested, please just go to my publications. First result, main result, I would say very nice result obtained during my PhD research, which is highly ordered monolayer of silica nanoparticle on solid substrate. And to best of my knowledge, this is the first time done that you get a large area monolayer over 1 × 1 centimeter square substrate. And what is the uniqueness behind my method? That I use a drop casting, but this drop casting technique is improved with a new thing by adding a sterile alcohol as assistant for the nanoparticle to order. And also our technique is a very simple, very cheap, that can meet the industry requirement. Okay, to get information about the structural arrangement of our nanoparticle, I also check it by GSAX, and also to be sure about my system, I use born-again software to simulate the detector image to know what is exactly happening inside my system. So this software is based on the stored-born approximation, and from the simulation, I obtained that my nanoparticle tend to order into 2D hexagonal lattice, and I assume a spherical nanoparticle with a diameter 50 nanometer. But to get information about the depth profile, if I have just monolayer or multilayer, I measured reflectometry. Reflectometry, as I said before, you study the nuclear scattering length density by varying the incident angle. And what I found a very nice modulation, which comes due to the monolayer nature. And what's interesting, that the nuclear scattering length density is variant according to a parabolic shape as I fitted the data. The second thing that I'm going to publish next week, it's about 2D ordered arrays of ferromagnetic cobalt ferrite nanodots, which has a hemispherical shape. And I check it first by AFM. And from the line profile, you can get access to the interparticle distances. Same, I did GSAX, and from GSAX confirms that also I have a highly ordered arrangement of cobalt ferrite nanoparticle, simulated using born-again software, and also studied by reflectometry. And from reflectometry, what I found this is the system. The sample prepared under a high temperature treatment, and during the preparation there is a very thick oxide layer separated between the particle layer and the silicon layer. For magnetization measurement, I measured magnetization as a field dependent, and what I found quickly, that the particle like to align when we measure if the sample surface along the field, but also at low temperature it shows in the other direction this nice opening at high and low field, which comes from the ferrimagnetic material, because ferrimagnetic material have 2 sublattices, and by adding these 2 sublattices we end with this opening. From the magnetization versus temperature, what's nice observed that there is some decreasing in the field cooling curve, which comes that there is some magnetic interaction between the nanoparticle. Okay, but to get information about the microscopic magnetization, I measured a neutron reflectometry at Maria reflectometer in Garching, Munich. And what I found, that the nanoparticle at saturation has a small in-plane magnetization parallel to the field, and at remanence it has a zero net magnetization. What is nice behind this technique, that you can calculate the magnetic scattering length density, the nuclear scattering length density, and you can get the magnetic moment per nanoparticle and compare it with the bulk material. So, last thing done on my PhD about depositing nanoparticle in pre-structure substrate. But first, I would just like to show how this structure substrate looks like. So, first of all, I checked it by GSAX, and we can see this nice pattern, which comes due to the intersection between Ewald sphere and the reciprocal lattice representation of the truncation rod. And here we can see just a line cut of these samples, and these grooves, or this substrate, has a rectangular lines with a periodicity and with a thickness with a specific height. Also, the system simulated by born-again, and to get information about the groove depth, reflectometry measured. Okay, first example, I deposited the spherical nanoparticle inside the groove, and we can see most of the particles tend to order inside the grooves with a two-dimensional hexagonal lattice with approximately 6 to 7 nanoparticle per line, and studied by GSACS to get more average statistical information about the lateral correlation in both directions along the lines perpendicular to the line. And as we can see, at both directions, it shows a very nice modulation along QY, which is an indication of the lateral correlation. Second example, depositing this Super Bowl nanoparticle. And first of all, I checked if I have a layering inside the groove, and by measuring reflectometry. And from the fitting of the data, I end up that I have a homogeneous layers inside the groove with the same thickness, and there is some magnet interaction between these layers. To get information about the lateral correlation, I measure GSACS, but at 3 different directions to get information if we have a 3D single crystalline arrangement of nanoparticle. And we end that our nanoparticle in plane tend to order into 2D hexagonal lattice, out of plane tend to order into FCC structure. The outlook of this work, because was this at the end of my PhD, I'm going to do it soon to study the magnetostatic interaction of these nanoparticles inside the group by using polarized grazing incidence small angle in neutron scattering technique. For magnetic properties also, as we can see, interesting, it's at the particle prefer to align along the trenches more than perpendicular to the trenches, and also it shows a small decreasing in field cooling curve, which comes due to the magnetic interaction between from layer to layer. Okay, let's take a small break and summarize what I did during my PhD. So I used different type of nanoparticle. First, nice results, get a very large monolayer over 1 × 1 centimeter square silicon substrate. Also 2D hemispherical cobalt ferrite nanodots studied by different technique, and also I could get also 3D arrangement of nanoparticle inside rectangular grooves. Okay, what I'm doing now quickly, since a few months after I finished my PhD, I started my postdoctoral research at University with this group. We have a nice lab there to synthesize different nanoparticle, and we are interested to characterize it by a lot of techniques, especially the large facilities around the worldwide, like DZ for X-ray and Oak Ridge or NIST USA for Neutron or ILL at France. So what is interesting, what I started to study the spindles nanoparticle, and I combine it with the spherical nanoparticle, we end with this nice system, which is called hybrids. So I'm going to study the magnetism dynamic of this system by perform TSAN technique at NIST USA and by Sans-Paul technique at ILL, France. Okay, what is my future vision of my research? What can be done with all my experience on nanoparticle, especially for my home country, Palestine? First of all, we can do a collaboration with PhD students registered in Palestinian universities, and this is done between me and Ghadir Hanbali during my PhD. She is a PhD student at Al-Najah University. She came for a short visit to Jülich, and she said, I have this material and I would like to characterize it. Then I offer for her our equipments in JCNS-2, and we had a very nice work which is published just during this month. The second thing also created the idea for the nanoscience research cluster with some collaborator from Palestine and from Germany, from Forschungszentrum, and also from Köln University. For long term, I'm planning to establish my own research group in Palestine by keeping a good connection with Forschungszentrum scientists and German universities. And also second thing, construction of an infrastructure. So I'm planning to have a lab with a simple equipment to start synthesis nanoparticle and to do the first characterization. For advanced characterization, planning to have a collaboration with Sesame at Jordan or DZ for X-ray, for Neutron with the FRAM2, ILL at France or NIST at USA. At the end, I would like to say thank you for Al-Quds University, my university where I started my education journey there in physics. Also, I would like to say thank you to all people in JCNS-2 to give me the opportunity to do my PhD and my master research. A lot of thanks to people in different institutes around the world also, and thanks a lot for PGSB advisory community and coordinators for giving me opportunity to present my work and what I'm planning to do in future. Thank you for your attention, and please, if you have any question or comments, don't be hesitant to contact me via this email address.